wanted to introduce Dr. Peter Sandwall from Ohio Health to introduce us to Detector's choices and different consequences. So I'm just going to hand over the stage to Dr. Sandwall. Thank you.
Yeah, my name is Peter Sandwall. I'm a physicist, clinical physicist in Ohio. Ohio Health is a large network. We're number 2 in Ohio. Number 1 is Cleveland Clinic. They have more hospitals than us. But Ohio Health has 11 hospitals in central Ohio and accelerators to go along with those hospitals. So I'm a therapy physicist. And this is actually a subject I really like, dosimetry, radiation dosimetry and measurements, because I think this is where physicists really have their value. One of my advisors always told me that a physician can impact a patient one at a time. A physicist can impact them all at once. When we calibrate the machine or when we commission the planning system, we're impacting all the patients that'll be treated on that machine. So it's really critical we do it right. So I'm going to go ahead and get started. I encourage you to ask questions in the chat. I won't get to them right away, but I will get to them. And there will be points where I'm going to ask questions that I hope that you will answer in the chat. And again, I'll prompt you for that. And this is on your syllabus. So we're gonna cover the definition of small field size. Even though this isn't really the topic, we're not going over small field dosimetry. We are going to just start with this definition. And that was one of the assessment questions, was how you define a small field size, because that impacts your selection of detectors. And we will go over kind of the family of detectors. We're going to go over ion chamber, diodes, plastic scintillators, these OSLDs, which can be classified as luminescent dosimeters, radiochromic film, and just a touch on gels, just so that to go full circle, nothing in depth there. Then we'll also, throughout the presentation, or throughout this, we're gonna talk about the use of the detectors in beam measurements, as far as output calibration, profiles, PDDs, and output factors, or they're sometimes called field size factors. I have some learning objectives. So after I've kind of broken them down into 3 classifications. These are different levels of thinking. So I want you to be able to remember, to understand, and apply. So these are the 3 things. I want you to remember the detectors that we cover, recognizing key characteristics. So that's the kind of the first order of thinking. Then I want you to understand, to be able to differentiate between the detectors by recognizing their limitations and their advantages. And then the real purpose of any education or any kind of learning is to be able to apply it. So I want you to be able to choose the appropriate detector for the desired measurements. So with your understanding and recall, then you can be able to apply this in practice. So like I said, we're not covering small field dosimetry, but we will define it real quick. So it's defined by a few things. It's defined by the loss of lateral charged particle equilibrium on beam axis. And that's something that's actually a really deep topic. and that's kind of why we're not going into it. It's covered really well in this technical report by the IEAE, and we'll just we'll touch on it. It's also defined by partial occlusion of the primary photon source. And if you think about it, the photon source starts at the target and then the flattening filter. And if you've got a field size smaller than your flattening filter, you're actually you're occluding, you're blocking some of that source. So that has a play in defining that. And then the detector, and that's what we're talking about today. And that's why we're bringing up this subject, is because the detector is part of the definition of a small field size. So the first 2 characteristics are beam related. The third is detector. And so that's why we're just touching on it. And like I said, this is covered really well in this TRS 483. It's free. It's published by the IEAE. I encourage you to digest it. It's a wealth of knowledge. And I also want to highlight the fact that this is covered in more depth in our SRS and SBRT course. So I encourage you to enroll when it's available, or when you're making that transition to using smaller field sizes in clinical practice. You were given a quiz when you enrolled. So Senji, can you give this as a poll? You were confronted with this question before, so hopefully it's a little review. So small field correction factors must be used, or should be used, when performing measurements for all field sizes that are A, smaller than 4x4, B, smaller than 10x10, C, have a full width at half maximum, less than or equal to 2 times the radius of the charge particle equilibrium, plus the largest dimension of the detector. D are smaller than 2 by 2. I can see that the majority of you are selecting the correct answer. And I see we're at 132. I'm not sure how many participants we have total, 137, 140. What's our total number, Senji?
We have 207.
Okay, 207. So it's up to 150, 154. So I'm going to get up there to close to 200 because I want to be respectful of time. And we do have a lot of stuff to cover. 160, the correct answer is winning. 160. We'll go with that. I know. I saw some of you are driving. It's totally cool. Like when we're all busy people and we've got a lot to do. So I even appreciate you guys taking the time. So we'll go ahead and end the poll. So I don't know if you can see that if that comes as a pop-up, but I'll continue with the presentation because the answer is C. So let's make sure it's very clear. And so the field size. The full width at half maximum is just a fancy way of saying field size because the field size is defined by the 50% isodose line. From that report I just shared, the TRS 498, the IEA report, the range of charge particle equilibrium or the lateral charge particle equilibrium, that range is defined by an analytical equation. They have it defined by TMR and they have it defined by PDD. Because TMR and PDD are essentially measures of beam quality or beam energy, the range is based off of that energy. Higher energy, higher range. For a 6x beam, with a PDD of around 67%, you've got a lateral charge particle equilibrium of about 1.1 centimeters. So that's getting one of the beam characteristics. Again, this is defined not just by the lateral charge particle equilibrium, but by the detector dimensions. So for simplicity, we're going to use the width of a Farmer chamber. And we'll talk a lot about Farmer chambers because they're my favorite. But the width is a little less than a centimeter. It's about 0.1. It's about 0.7 centimeters or 7 millimeters. So we use that equation, a full width half max less than or equal to 2 times 1.1 plus 0.7, and you get about 2.9 centimeters. And that's where you'll hear this often quoted value of about 3 by 3. It's for a 6x beam measured with a spherical detector, the width of a Farmer chamber. Now, if you look at the largest dimension of a detector, a Farmer chamber is actually larger than its width. It's longer than that. So that's where you might get that 4 by 4 value with a Farmer chamber. But I just wanted to break down that question and then also point you to the TRS 498 if you want to learn more about it, because you'll see that field sizes and detector dimensions are a big part of measurement. So what we are covering, let's get into what we are covering in this lecture. We're going to cover volume detectors, we're going to cover point detectors, and we're going to cover spatial detectors. And I'm sharing this book. This is the book that I studied in graduate school. It's not medical physics focused. It's actually more broadly radiation focused. People use it in all areas of radiation science. So from nuclear engineering to space physics. And I think this is a great book. If you can find a PDF copy, it's a great reference. So we're going to go over, for volume detectors, we're going to go over gas field detectors, specifically ion chambers, semiconductor detectors, specifically silicon diodes. It's important to note that there are different gas field detectors, the GM counter being one, proportional counters being other. And for semiconductor detectors, there also are MOSFET detectors. But we're not going to cover those. We're going to go over ionization chambers, silicon diodes, and we're also going to touch on plastic scintillators, only a little bit, because they're a new and upcoming detector, and they've got some cool characteristics that make them really useful, especially in small field dosimetry, which again, we're not covering, but we will cover the detector. Some point detectors, and that's a kind of a misnomer because they still do have a volume, but they're very small, are the thermoluminescent detectors and the optically simulated luminescent detectors. And those can both actually be classified as luminescent detectors. Then as far as spatial detectors, we'll go over radiochromic film, also known by its trade name of GAF chromic. It's like Q-tips. You can create radiochromic films that are different than graph chromic, but graph chromic is the most well-known brand, and it's kind of that name is kind of synonymous with with radiochromic. And then we're going to touch on gels, but we're not going to go into too much depth. That's kind of more of an experimental thing if you're into that, but most of us are clinical and we don't have time to work in a lab. If we do, gels are where it's at. I'm a big fan. Let's talk about detectors or dosimeter characteristics. Another reason I shared the title of that book, Noel's book, The Measurement and Detection of Radiation. So detection is just discrete, yes, no, is it there? And our Geiger-Muller counter is a good example of yes, no, is radiation present? But really what we're talking about today are actually dosimeters, things that measure. So the meter, so to measure the dose. So I just want to make that classification. There's a difference. So these are the characteristics that we need to know about each detector or dosimeter. So the environmental dependencies, and those can be temperature, pressure, humidity, heat. Temperature and heat are the same thing. I know, I saw that. I was like, what did I do there? But hey, I'm human, which are well defined by things such as the temperature pressure correction factor for used in TG51 or other calibration protocols. And those are based off of the ideal gas law. Essentially, pressure times volume equals the number of atoms times the ideal gas constant times temperature, or PIV. I love this equation. We're physicists. This is the good stuff. But how that plays into the detection elements or the elements of interaction within a volume, and also temperature plays into effect the mobility of charge carriers in solid state, and we'll talk about that later too. So dose rate dependence, recombination, saturation, linearity. Are there saturation effects? How does that affect the linearity of the response? Is it superlinear? And this is kind of a showing you that some detectors actually have a superlinear response after use, TLDs being a good example. Many chemical dosimeters, thinking gels and radiochromic film, they have saturation. After a while, their sensitive elements are exhausted. So, but obviously we want a linear relationship. Energy dependence are based on the material that they're made out of. Do they have a threshold response? The directional dependence are the sensitive elements subject to orientation, whether or not it's got it at an angle, how is it going to respond differently? And then obviously spatial resolution and size. And we'll talk, we're opened up with that with regard to how a detector impacts small field measurements. We'll talk about the differences in size of detectors and how that impacts our measurements. I know that I talk fast, and I'm sorry if I'm talking fast. So this is part of why I've got it. The animations is to slow myself down. But I hope that if there's something that needs clarification, you'll put it as a note to yourself in the chat so I can come back to it. So the ideal dosimeter, it should be accurate and it should be precise, the ideal. And, we've probably all seen this kind of chart before. There's a difference between accuracy and precision. A precise and accurate is dead on the bullseye all the time. A precise but inaccurate is reproducible, but off the mark. And the truth is, most dosimeters are precise but not accurate. And now they have varying degrees of accuracy, but if it's precise but not accurate, that's okay. We can apply correction factors, and that's what we do. Ideally, we'd have a low detection limit, a large dynamic range or a large measurement range. We'd be able to cover all the values that we're interested in. A linear dose response over our measurement range. No dose rate dependence. Tissue equivalent. High spatial resolution. And the reality is, there is no ideal dosimeter. There's the real dosimeters that exist, and most of them are compromises that achieve some of these objectives, but not all of them. And it's important to know when we're compromising and how to correct for those compromises. The roles of dosimetry in radiotherapy, selecting the right detector starts with what you plan to do with it. So how do you plan to apply it? So what's your application? Then you look at your tools. Okay, this is a nail. I need a hammer. So you've got these are kind of just a schematic of two different classifications. One of them is using a phantom, whether it's a water phantom, and collecting dosimetric data or calibrating the beam. And the other is patient measurements. And what you intend to do with the detector really defines the detector you should be using. So whether it's beam calibration, profiles and depth dose curves, field size or output factors, in vivo measurements, those are all things that define the detector you're going to use. Or end-to-end testing, which will be covered further next week. How is that? What's the best tool for that? So what would you use for output calibration? I'm going to go ahead and type in what you would use for output calibration, and just let's see some things. All right, farmer, I see farmer. Farmer's my favorite. I love the farmer. So absolutely. Yes. And ion chamber is a farmer. So you guys are all on board with this. This is great. What about profiles and PDDs? CC13 diodes, semiflex, CC13. This is great.
Yeah, that was my friend.
CC13 is a small volume chamber. SNC 125. This is great. So we're on the same page. So a lot of this is going to be reviewed. That's great. What about measurement of the penumbra? If we want really sharp penumbras, pinpoint small diodes, pinpoint diode is, I just take diode. So we're on the same page. What about in vivo dosimetry? What would we use for in vivo? You can use the GAF chromic. That takes some practice. This is good. And MOSFETs. Oh, I see MOSFETs. Semiconductors. Very cool. And those are really, really small. They just have a lifetime. We're not covering them today, but they're cool. What about end-to-end testing? TLD, GAF chromic, pinpoint, film, gels, detector arrays, and these combinations with using multiple detector elements, 100%. So thank you for participating in this checkpoint. And we'll come back to this. Let's just get started with the detectors now. So gas field detectors. They're a class of detectors. They're a family. As physicists, we're typically responsible for knowing this curve, the gas amplification curve. Too low a voltage to a gas field detector, and you've got recombination, so you can't get a good measurement. Too high a voltage, you've got continuous discharge, kind of saturation, where the thing turns on and it won't turn off. Gas field detectors kind of work through the simple process. You got radiation interactions creating ion pairs. Those ion pairs are collected by an electrode. What we're focused on today is the ionization region, just that one region. And the reason why the ionization chamber is well loved in radiation therapy is because of this flat response. It doesn't change. It's pretty straightforward. The response doesn't change for that region of, like I said, it consists of a gas volume between two electrodes connected to a high voltage, typically between 100 and 1,000 volts. For ion chambers, farmer chambers, it's 300 volts. There's some that are more, but that's pretty much that's the range. So we're going to talk about cylindrical ion chamber, the farmer first. This graphic isn't really a picture of a farmer. It's just a picture of a thimble chamber. You've got the sensitive volume, which is that air, the central electrode, the thimble cap, which is the wall, and you've also got an insulator or guard ring. So the ion pairs, both positive and negative charge carriers, are created in the volume by ionized radiation and attracted to the electrodes, creating a current which can be measured by electrometer. And this book, I don't know how much Addicts contributed to it other than the fact that he has this long lineage. He's written so many radiation dosimetry books, and this is clearly an evolution of his previous book. But this Fundamentals of Ionized Radiation, again, if you can get a PDF copy of this is a great book. There's also worked solutions for problems in it, which are great, but it covers a lot of this stuff in more detail. So, and that I like that cover picture because it's a Monte Carlo picture of a farmer chamber. And the sensitive volumes of ion chambers vary from 0.01 cc to beyond the farmer chamber of 0.6. And the nominal response of the farmer is what I really like because it's stuck in my head. 20 nanocoulombs per gray for 6 cc, 0.6 cc. I think having things like that in your mind, sanity checks, I think this is important and part of good practice. So let's talk about the farmer chamber. The 0.6 cc cylindrical chamber Where's its name come from? Name comes from Frank Taylor, a farmer. I like history and paying homage to our forefathers. 1912 to 2004, he had a good life. He studied RF propagation in the ionosphere, astrophysics or radiophysics for his PhD. He used this knowledge in the design of early accelerators, and he installed the first gantry man-made LINAC, installed in 1963. So the man did some cool things, and his many contributions are honored with his namesake Detector, which was an evolution. He didn't just make it out of thin air. He made it the condensation chamber and slowly improved and iterated until he published this final version in 1972. And what I like about this picture too is it shows the uncertainty in the air volume, 0.61 plus or minus 0.01. And that's important to remember. Like, not everything we do is perfect. There's always an uncertainty, and knowing that uncertainty is really essential. And it's stating that uncertainty. But he stated it right then and there, and that's why we have different calibration factors for the chambers, because there are slight variations in manufacturing. The farmer chamber is now just kind of a name for a class of detectors. And there's all kinds of different types of farmer chambers. There's this A12, which has kind of got more of a hemispherical tip than the traditional pointed tips. But you can see that the geometries are slightly different. The volumes are all essentially or close to 0.6 cc, but they're not quite. And one of the big differences between them is the materials that they're manufactured with. And this is an important thing to pay attention to, because the material impacts the energy sensitivity. So each one of these chambers, they work essentially the same. However, their dynamic range may be a little different. And where it comes into play with a farmer chamber is actually in the low energies. So optimized materials can work down to 30 keV. Some of these can only work down to 120 keV. So it's something to be mindful of. Not every farmer chamber is exactly the same. So be mindful of the material composition, and we'll talk about that on the next slide. Well, maybe not the next slide, the following one. This one, I'm gonna extol the virtues of the farmer chamber. Why I love the farmer chamber. Well-characterized response, long-established correction factors for recombination, environmental factors, and geometry. And that's what these are. P-ion, P-elect. Polarity is actually, it's a function of geometry. As you change the polarity, you're affecting the geometry of the collection volume. So that's why I kind of want to highlight that. That's what you're looking at. You're changing the electrode. You're changing the geometry of the electrical surface. So the energy dependence are known, but they're really good. It's essentially flat, depending on the chamber you use. It's really flat down to the KE, which means you can use it to check your OBI or to check your XVI. It's just a really robust chamber. And this is actually a published version of somebody's copy of a farmer chamber. They built their own, and it's still relatively flat. And it depends on the how deep you dial in. But the farmer chamber is really dependable, and I love it for that reason. And again, I also have that burned into my brain, the 20 nanocoulombs per gray. So I know that when I'm checking a 6 MV beam at 10 cm depth, I'm going to get about 14 nanocoulombs, accounting for temperature and pressure and the small variations between manufacturer. I have a sanity check. So I know that I'm not going to, if something's wrong or something's out of whack, I'm immediately going to be able to tell. So that's one of the many reasons I love farmer chamber. I want to bring up the fact that, the collection efficiency comes at a cost. The volume averaging limits the utility, especially with small fields and in the penumbra. And so then we're going to talk kind of more about smaller detectors. So there's all kinds of different ionization chambers. And some people say that you can get a response of plus or minus 1%, and that's how we calibrate our machine. But the reality is the uncertainty is different than that. And 2.5% under optimal conditions. So we want to do our best to get it as close and tight as we can, because there is uncertainty in the calibration process, and we need to respect that. It's important to understand your chamber and its limitations, primarily due to the material and composition and geometry. And like I said, the Farmer chamber has been well studied. This here is a Monte Carlo of the collection efficiency, and it's showing kind of the field strength there at the bottom. You can see these darker areas, C and D, and at the tip. If you flip the polarity, it changes those field lines. Here's kind of a really cool study where they looked at the responses of different detectors, these different types of farmers, and they showed the response map, the scanning chamber. And what you'll see here with the scanning chamber is you see the size of the thimble. The active volume is much smaller, and the region of response is smaller still. So that's why it actually approximates a sphere. It gets a lot closer to a spherical volume instead of like a true thimble where the length is different than the width. This pinpoint one right here, there's two pinpoints. You see 31006 and 31014. These were made with different materials. This old model, the 06, was made with a steel electrode. And we had to learn the hard way that steel does not equal aluminum. And there was an over response to low energy. So when you collected output factors with increasing scatter, increasing contributions from low energy photons, you got an over response. And that was learned the hard way. Again, it's important to know what the materials of your detector are, because they may look the same on the surface, but they may respond differently due to their composition. And like I mentioned before, these different Farmer chambers, some are made with plastic, some are made with graphite. That changes the response, especially at low energies. So more about ion chambers. So parallel plates are also ion chambers. They're great for surface measurements. They are recommended for low energy electrons. Little chambers get you pretty good, but you can cross calibrate a parallel plate with a high energy electron beam. And the cool thing about them is you're able to, their point of measurement is near the top, near the entrance window. So that effective point of measurement, though, it may vary depending on the manufacturer. So again, this goes back to the knowing your detector. So you can have one that looks exactly the same, but they may be different underneath. Here's an IBA detector, and it's showing kind of the air cavity where the collector is and the body. And this was published in a beam quality conversion factor for parallel plates. And what they also did was they showed that those changes of manufacturing can occur without customers' knowledge. You can have, here's two Extradent A11s with different manufacturing processes. And you can see here, you've got screws and you've got different guard electrodes. This is going to change the response of your detector depending on what you're doing with it. So inspecting your detector is on you. The manufacturer, you hope and you expect them to give you that information, but that pinpoint detector with the steel electrode, that was discovered by a physicist out in the field who cross-compared their measurements and was like, wait a minute, what's going on? This is different. These detectors that look the same respond differently. So be aware of these subtleties. So kind of wrapping up the ion chambers before we move on, let's talk about the pros. It's well understood. So many people have done Monte Carlo on ion chambers. It's super cool. And there's a wealth of material out there. You can get within 1%. I put an exclamation mark because it's beware of hubris. Always check your measurements, and cross-check your measurements. And it's got a low energy dependence, meaning you can use it on just about any beam that you're encountered with as a therapy physicist, which is really cool. Some of the cons. This is listed as a con, but it's not really. You need a calibration just to get a calibration coefficient. You get the one that you get from your manufacturer. The detectors change over their lifetime. And so it's important to get those periodically recalibrated because your detector may change over time. This Extradent A12, friends at the MD Anderson, they know that those have a lifetime. They see it over time. The plastic hardens and eventually they fail. So getting them checked and ensuring that their response isn't drifting too much is important. But that does cost money, and that is frustrating. And then size limitations. You can only get so small with an ion chamber, and we'll talk more about that now. What are the alternatives? So with beam scanning, that's when getting a small chamber really is important. And there are many of you listed the CC13, and you also listed the SNC 0.125, essentially very small difference in volume. So very small difference in volume, but very similar. The micro chamber, CC01, and those refer to their size, 0.13 cc or 0.01 cc. Here's a picture of them. Many of you, I'm sure, have worked with them, but these are good for scanning. This picture is just showing the difference that you get because of the detector response and the volume averaging. The CC13 and CC01 are going to give you different penumbras, and this is with a 10 by 10. So selecting the detector that you need or that you want to compare with the data to is important. This difference, while subtle, may not be what you're looking for if you're comparing to gold beam data that's been collected with CC13 data. If you're going to want to compare apples to apples, you're going to want to use similar measurement devices. I've also got this difference between the CC13 and the CC01 based on your responses. I think you guys have used these detectors, so you can see here the 13's got a much flatter curve. And that's just because of its collection efficiency. If you're going to use a CC01, you're going to need to slow down your scan speed and to get the same statistics, to get the same smoothing. So that your curve quality is affected by your scan speed and your volume. You get a larger volume, you can scan it as fast as you want. Smaller volume, you better slow it down to get equivalent. When you're scanning profiles, it's important and you're measuring the penumbra, it's important how you set it up. So be mindful of scanning orientation. Like I mentioned before, this CC13 approximates a sphere. So it doesn't have that much of a directional dependency, but others do. So whether you scan lengthwise or you scan horizontally, that you're going to get a different penumbra. And depending on the chamber that you use, like I said, the 0.125 begins to approximate a sphere, but still you can get a little difference. So something to be mindful of when you see some different profiles. So those 13 or 0113 or 13 cc's 0.125, they approach that spherical geometry, but others do have that volume effect. So how do you get the sharpest, most accurate penumbra? You want to use the smallest volume. And what's smaller than small? I know that you guys already are on board with this. It's diodes. And I'm showing here the sun point diode, the edge detector diode. And this is showing relative to matrix or the 729 ion chambers. It's just really, really small. So you can get a really clean penumbra with a diode. So there are caveats to their use, but diode dimensions are so much smaller than gas fields because of the solid densities, because of the density difference in air. It's thousands of times greater, not just 1,000 times, but thousands of times greater. Let's talk about these semiconductor diode or detectors. The semiconductor, it's this middle ground. You've got conductors with a conduction band and a valence band, or you've got an insulator where there's a large band gap between the valence band and the conduction band. Semiconductors have a gap that's with a small energy gap between an almost empty conduction band and an almost full valence band. So the most common in radiotherapy are the silicon diodes with about 2 to 3% uncertainty. So how they're manufactured is lightly doping silicon with phosphorus, which is N-type, but majority carriers are electrons, or boron, P-type, majority carriers are holes. Here's a picture of that. So it's a lattice of silicon with impurities. So in this middle one, you've got the phosphorus with an extra electron that's free floating in the conduction band, or you've got it doped with boron with one fewer electron, and it's got a hole. It's got a hole in the valence band. So you've got different ways to transfer those electrons. So then to create a semiconductor, you heavily dope an area with several orders of magnitude of the opposite to create a depletion zone. And this isn't showing one or the other. This is actually a PIN, but this is what's created. If you've got significantly more phosphorus on this area than you've got the boron on this other side, you're gonna get this depletion zone. And I'll show you how they look in practice. So, like I said, here I wanted to show this picture over here. So you've got this. The whole substrate is doped, and then you've got this highly doped area, which creates this depletion zone. And this is how they look for most radiation detectors. But this creates an electric field across them that's intense enough that you don't need to apply an electric current. So you don't need to apply an external bias. Some diodes do use bias, but they're measuring resistivity. They're not measuring the flow of electrons. And in principle, it's also important to note that in principle, because what you are doing is you're ionizing things, you're knocking out electrons, and then they're recombining. You're damaging the semiconductor, so that gives it a lifetime. And unless it's been hardened ahead of time, which a lot of p-types are hardened, you get a drifting response over time. And it's just important to know what you're working with and know that response that you're getting may change over time with use. Some of the limitations with silicon diode, that high sensitivity comes at a cost. It's highly sensitive because it's a dense material, but it's also a higher atomic number. It's almost twice that of the effective Z of air. So it's 14 versus 7. And we know the photoelectric effect is dependent upon the Z. So that means that you're going to get a lot more low energy photon response. So when you've got increased amounts of scatter, whether that's at depth or out of field, you're going to get an over response. So this is one of the reasons why sometimes the diode's not the right detector for the measurement. Also about diodes is they have an energy response. So increased heat, you're increasing the charge mobility, you're changing its sensitivity. And it's been shown that it's really important when you're using diodes for in vivo dosimetry. So you put it on a person's skin, that's a significantly higher temperature than ambient. So if you calibrated your diode at an ambient temperature and then you're using it on a patient at close to 100 degrees, you're going to get a different response. And that's something important to be aware of. Another thing is the geometry. So we've got different geometry detectors. You've got these flat ones that have buildup, and they've got a strong directional dependency. And then you've got these spherical ones, which have less of a directional dependency, but still, if you turn them up, it's going to give a different response than if you have it on its side. So it's important to kind of understand the geometry of your detector. I'm going to do my best to kind of speed up, or what do I do, Senji? I haven't run into this before.
It's okay. It's okay. I think we usually just try to go. I think you can go as long as you could, and then if people have other duties, they can.
All right. My apologies.
It's all right. I've been enjoying the talk.
I'm really good at keeping the time, but I actually really like this subject. So sorry about that.
It's great. It's great. It's great. Yeah, we're
okay.
Learning. Yeah. Thank you.
Take
your time. Yes.
Okay. So I just showed you two different geometries of diodes. So there's those with the buildup, but there's also the inherent buildup of the casing. So depending on how the material or the diode is encased, that really changes its sensitivity. That casing can offer, or it could be a filter. It can filter out the low energies. So you have bare unshielded detectors that still have that casing effect, but it's selected based on the energy range that it's used for. So you've got whole families of diodes, and these are different diodes are designed for different energy ranges. You cannot use a low energy diode for a high energy beam, but you can use a high energy diode for a low energy beam if you need to, as long as you're not using it in the buildup region. And this shows the kind of the different responses you'll get with different diodes. So again, cross-comparing your measurements and knowing the diodes you're working with is important. They're not every one is equivalent for all beams. Let's talk about the pros and the cons of the diodes. And that means that they can be packed into these kind of arrays. And this has got 1,500 diodes in this one. And this is not a Sun Nuclear commercial, but they do make small diodes. So they put them in different arrangements. They pack them in different arrangements for different applications. Rapid readout, you get an instantaneous result. You get an instantaneous response, which is really nice. And you don't need to apply an external bias. So those are really good. Those are nice things. Some of the cons, the temperature dependence. That's a serious limitation, especially if things are running hot, especially hotter than when you calibrated them. Dose rate dependence, there is a recombination with the charge carriers. So there can be a lower response with the higher pulsed beam. And then energy dependence, we talked about that, the silicon versus the air, that's going to give you a different response. So they operate through luminescence or through fluorescence. And I can actually talk all about this one slide. So I'm going to do my best to go quickly. You get light that comes in, it excites a molecule, and then there's some internal conversion, a little vibrational relaxation, and then emission of a different color light. The way this works in scintillators is they've got a whole family of compounds built into this plastic, which downshift the radiation from high energy to lower and lower energy until it comes out as light. These are kind of a newer thing, a newer commercial application, but they're really cool because they're nearly tissue equivalent. They're made of similar materials as us. So you don't have those same issues like you do working with silicone. It's hydrocarbons. In the way they work in practice is you've got a light pipe, which is like a fiber optic light guide connected to a small sensitive element. And then the light that's released from that sensitive element is proportional to the dose that's delivered. There are some sensitivities to this. So we'll talk about the good things. Small volume. Those detector elements can be within 1 by 1 millimeter or 1 by 3, the newer W2. There's another manufacturer, but I haven't studied their device yet. It's very new. Near water equivalents. It's got a very similar composition as us. It's a hydrocarbon. It's not going to be not a very high effective Z. So it's got no dose rate dependencies. So it's cool. Some of the cons. There's noise from shrink radiation. This is a whole other subject, but essentially when you got electrons moving fast in a medium, they give off blue light. So that creates a background noise, and it's corrected for by calibrating. Again, you can have a precise device as long as you're correcting for it to get the accuracy. There are also changes in sensitivity. There's polymerization that occurs in that plastic, which darkens it over time. And we'll talk about that in relation to GAF chromic film. But that changes over time. And then there's limited vendors. Really, it's only Standard Imaging for the W1 and W2. And this new company, MedSynth, they just developed something. I don't know if it's out there yet, but this is an up and coming device, small volume, near tissue equivalent. It's cool. On the topic of light, and I am really sorry about going over on time, but I hope you can stick with me. So on the topic of light, there's luminescent dosimeters. So the way that these work, there's two main ones, OSLDs and TLDs. They work very similar to semiconductors. You've got a lattice, and you're going to bump electrons from the conduction band to the valence band, or from the valence band to the conduction band. When they're in that conduction band, they fall back down, but they get trapped. And when they're trapped, it's essentially a storage of the energy that they've been exposed to. When you expose them to either light or heat, so you essentially release those electrons from those traps, where they then come back down and they recombine. And then during that recombination and relaxation, they release some light. And that light's proportional to the amount of radiation that they were exposed to. There's a glow curve for TLD. It's a complex. It's based on the temperature that you heat it to. You heat it over time, and you integrate that area to get a value, and then you correlate that value to dose that it was exposed to. One of the advantages over OSLDs are the fact that you hit them with a laser. Depending on the intensity of the laser is how quick you're going to get your result. But you integrate that area into the curve, and you correlate that volume of light emission to dose that it's been exposed to. I call them point detectors, but they are a small volume. TLDs are the most well studied. They've been used for years. They use this principle in archaeology. That's kind of cool. but they're commonly little chips made of lithium fluoride doped with magnesium and thallium. And like I mentioned, you put the TLD and you heat it. You've got a thermocouple here and you heat it. And depending on the time, the way that you heat it, you're going to get light emission, and you're going to measure that, and that'll be proportional to the dose. You can get uncertainties within 3%. A lot of people will report 5%. It's definitely a variability. So uncertainty is something you always strive to minimize, but it's there and you need to recognize it. The cool thing about them is they're small. The Rando Phantom was designed for use with TLDs. So it's got all these different holes so you can actually measure all these different points in a Phantom, or you can use them on humans for in vivo dosimetry. OSLDs, again, they operate similarly to TLDs. They're made out of a different material. They're made out of aluminum oxide, but they operate in a similar principle. But instead of heating it, we're shining light on it. We're hitting it with a laser, and then it's releasing another light, and that light is proportional to the dose it was exposed to. There's this system that's sold by Landauer that a lot of people use, and this is about 4 of these might fit on your thumb, depending on the size of your thumb, but they're small. These are really well characterized and used for in vivo dosimetry now at this point. And this is actually a study where they looked at the different places it was used at, the different types of treatments it was used for, and they were able to really get good reproducible results. But it's important to be mindful about your placement of the detector. Only having a single vendor is a limitation, but I did see that Bark in India, they built their own system from the ground up. So hopefully there'll be there'll be cost competitiveness in the market. Pros and cons. Start with the good. TLDs are energy independent, relatively. They have neutron sensitive models. They're reusable and they're well studied. Pros of OSLDs, you can read them out multiple times because just where you shine the laser, that's where you get the response from. So you might have an area that you can shine multiple laser points on, and that's what they do. Sometimes they'll reread them. Rapid readout, much quicker and less complex than the glow curve or the TLDs. They're reusable, and you have a persistent record. The cons of TLDs, you only read them once. They require a significant time for readout, and they got a super linear response with reuse. Those traps and those recombination centers, they change over time. The more radiation you expose them to, the less those centers that are available, and they become more sensitive over time. Cons of OSLDs, they're higher effective Z than TLDs. They're aluminum. So you're essentially working with a metal detector. And so they've got a stronger energy dependence. It's kind of funny. Those two cons are actually the same thing. So that effective Z gives it a stronger energy dependence. Film, radiochromic film. I don't say GAF chromic. I say radio because GAF chromic is just a trademark. Radiation incident to an active layer induces monomers, small molecular units to join, creating polymer chains. This is the secret sauce. And it's not a secret. It happens everywhere. If you've got an older car and you've noticed that the plastic in your headlamps has become opaque over time, that's because there's been polymerizations from the UV light. So this is something that we've known about for years. Radiation induces polymerizations in plastic. So we're taking advantage of that with radiochromic film. So that opacity, that change in opacity can be calibrated to be proportional to dose. And we can get about 2 to 5% uncertainty with the proper protocol. And that's what I'm going to be I want to emphasize this. Film is not to be taken lightly. This is not radiographic film, or this is not like silver halide film where you needed the processor and all that. But this is still a very sensitive process. And it depends on it goes down to even like what light channel you choose to look at with the film. And there's been methods to integrate these light channels, and that actually reduces some of the dependencies. But creating a calibration curve is not a small feat and should be done very carefully. So one of the other things to bear in mind is that polymerizations continue to occur after radiation. So those chemical reactions, they're ongoing for up to a day. So being very consistent, waiting at least an hour, and then up to a day or even more if you want, but being consistent in that time period. If you're going to wait an hour, always wait an hour. If you're going to wait 3 hours, always wait 3 hours, because your response will change if you wait different varying amounts of time. So it's something to be very mindful of. So it's more of the subtleties of radiochromic film. I'm going to hammer one specific point. So those active materials, they're crystals, and they're rod-shaped. They're rod-shaped crystals. Here's an electron microscopy image of them. So they're these little like fibers, kind of, you can think of them as. They orient parallel to the coating process. So when you're making a film, it's not just the active layer, it's also like a polymer layer on top of it to keep that intact. And when it's coated, because of the direction of the fluid flow in the coating process, it orients those rods. So they become light polarizers. And put that in bold because polarizing. So especially following radiation, they polarize the light. So that polarization, it creates a strong directional dependence of the film. The film is different if you measure it in landscape or in portrait versus landscape. It is not the same because it's a light polarizer. And further, because of the way you scan, you can see here you've got a lamp that kind of runs across, and you've got a mirror, but then the lens, the way it focuses the light for the readout, it creates a lateral response artifact. So the measurement in the center of the film is not the same as the measurement on the edge of the film. And so you just need to know about these things so you can correct these things. And this has been actually well described, and how to correct for these things have been well described. I've included all my references embedded in the presentation, so you can use these references. But film use is not to be taken lightly. It's not just let me do this and it'll work. If you really want to get dosimetry out of it, if you want to get measurements and not just detection, it takes some effort. So the pros of film is extreme spatial resolution. You get down to micrometers. A large measurement area, you get a good spatial, and it's tissue equivalent. It's made out of hydrocarbons. The cons, there's batch to batch sensitivity, so you need to create a new calibration for each batch of film you get. There's this light polarization, so you want to be really mindful of your process, and it requires a delayed readout. You don't get a You must recall where they start with the 10 by 10, and then they do their spatial measurement. And you've got the 10 by 10 over here, which is allowing you to correct for that lateral response. This is a link to an efficient protocol, but you got to adhere to a protocol if you want it to work for dosimetry. If you're going to just use it for light to rad field or star shots, okay, no problem. But if you actually want to do IMRT QA with it, it takes some time to set it up right. One quick slide about gel dosimetry, and then we're almost done. We're on the home stretch. And gel dosimetry is kind of like near and dear to me. It's what I study in my dissertation, and it's what I still like to play with. It's a really cool research topic. So it's an active area of investigation. It's truly a three-dimensional detector. I mean, you can create an anthropomorphic phantom. This is showing a kind of a head that's been filled with a gel, and then IMRT to the head. You actually get a three-dimensional distribution of the radiation deposition. It's pretty cool. I'm mostly talking about polymers too. There's RT Safe. They provide kind of a end-to-end testing on a per fee basis, but they use polymer gels. And there are several types. My gel is actually not polymer, but the polymer is the most common, but it operates the same as the radiochromic film, and the same as the darkening of your headlamp plastic. High energy radiation induces polymerizations, which changes the opacity of the gel. It also changes the magnetic properties. And this is kind of showing different doses and how the gel changes with different doses. The major limitation is the complexity of manufacture. It takes time and effort to actually learn to use it. Same as film. Film is a little bit more well established. There's lots of different gels out there. So it's a little bit more of a research project. And also the readout systems. You can read them out with an MR, or you can use an optical. There are some at Duke, especially they're working at obtaining images with cone beam. So that would be more practical, but it's still one of those research things. I'm just plugging it because it's a special interest. So we are kind of at the end. So I wanted to review our learning objectives. I wanted you to be able to remember, to understand, and to apply. So I hope that you're able to identify the review detectors, recognizing the key characteristics, differentiate between the detectors, recognizing their limitations, and choose the appropriate detector for your desired measurements. So I have a couple more slides. So I'm asking for some engagement here. So what would you use? So go ahead and type in what you would use for the farmer chamber for, or why would you use, why would you use the farmer chamber? Tell me one good reason why you would use the farmer chamber. Jorge's on my wavelength. This is, yes, Islam too. These are all good reasons that you would use. These are all good reasons. And there are different reasons, but the well-characterized, the well-studied is the one that I put up. And that's the thing I'm just putting these, but I want you guys to engage with the content and engage with me. I can't have conversations with all of you, but I can see your responses and I enjoy them. Small volume chamber. Why would you use a small volume chamber? Less volume averaging, definitely. Less. What about a diode? Small volume, high efficiency. You get you high efficiency. It's good. Okay. OSL or TLDs. Why would you use them? Well, I'm gonna just point measurement. No wires. You don't have to worry about anything. You just put them down in a place. And then film or gel. Why would you use a film or a gel? 3D, end-to-end, spatial. Yeah, you can characterize gradients. This is the one where you can really like dial in. And film, people do also use film for electron PDDs a lot. They're a good one. You just have to set it up right. So why wouldn't you use? This is that whole apply part. Why wouldn't you use a farmer chamber? Large volume. Yes, volume averaging. What about a small volume chamber? Why wouldn't you use it? Go lower collection efficiency, and there are different reasons. Diode, why wouldn't you use a diode? I'm looking, there is one thing, there's different things. Temperature dependency. There are dependencies. There are several different dependencies, so that's why. And that's really comes from the fact that they're not tissue equivalent. What about, why wouldn't you use an OSLD or TLD? I'm going to take that one. The readout system is a big part of it, and the system cost. Yeah, and you've got ongoing maintenance, and it's not real time, and you need time. What about for film or gel? Why wouldn't you use that? I'm going to go with that one. I mean, yeah, it's hard to use. I mean, but you can do it, and that's the thing is we're physicists, so there's nothing stopping us from doing very precise measurements and doing reproducible measurements. Time is what it takes, though. So you have the time to invest in it. So films and gels are time consuming. These are the same questions I asked before. I saw you got the answers right, so I'm just going to kind of move through them. The output calibration, the farmer chamber, PDDs and profiles, small volume chamber, sharp penumbra, you're going to get with a diode, in vivo dosimetry, OSLD, TLD, end-to-end testing, film, gel, or detector array, and end-to-end testing is coming up next week. So almost done, because last but not least, always check your work. Always check your work. If you get a measurement you don't like, you get a response you don't like, measure it again before you make an adjustment. Check it, and check it twice. Cross-check your detectors, understanding their limitations. Use different ion chambers for the same measurement. Collect those output factors with different detectors. Are the responses, the difference in responses as you expect with your knowledge of how those detectors respond? Validate your measurements by comparison with published or vendor supplied data. Or last but not least, call a friend. If you don't have the comparison data, call a friend or write a friend. And with that, I want to thank you for your time. And I want you to remember that you have a friend in Ohio. So thank you.